All right, so talking about liquids and properties of liquids, we're mainly going to be talking about vapor pressure. Vapor pressure. So let's look at this diagram. Yours is better on your page. So what do you have right about, let's see, here? That's at 760, and this is millimeters of mercury. So what's special about 760 millimeters of mercury? It's 1 atmosphere. It's called the standard pressure, okay? So vapor pressure is the pressure due to particles of a substance in the vapor phase above its liquid in a closed container, all right? The next page actually has, let me show you real quick. This is what occurs. If you have, say, for example, water in the liquid phase, you put it in a flask and you stopper it, some of the particles from the water are going to escape to the gas phase. That just naturally occurs. And eventually, and then some of them will go back to the liquid phase, and eventually when we reach equilibrium, we'll have a constant pressure of the water above the liquid, okay? This was open to the air. What would eventually happen to all of the water? It would evaporate. That's what happens like with puddles on the ground and stuff like that. It eventually all evaporates. But if we keep it closed, obviously the gas particles can't escape. But all liquids will have a little bit of the particles above it in the vapor phase. All right. So let me go back to this diagram. So looking here, we have diethyl ether, which is this substance, ethanol, or ethyl alcohol, and then water. All right. Let me draw out these structures for you so we can kind of talk about the vapor pressure. Oh, you know what? I'm gonna show this later. I'm gonna draw it now. All right, diethyl ether. Now we have some hydrogens with carbon. There's diethyl ether. We've got ethanol. Which looks like this. And then I'll draw water, even though you should know what this looks like, but I'm on a roll. All right, so looking at these structures, what can you say about their boiling points, their predicted boiling points? Don't look at the graph, just look at the structures. Which one should have the highest boiling point? Based on the structure? Why are you guys saying diethyl ether? Ooh, I like that you said that because you're very wrong. Remember, when you boil something, when you go through phase changes, what are not breaking? Bonds are not breaking when you go through phase changes. The only thing that's being overcome are the forces between the molecules. So you need to think about these molecules and how they're going to interact with another one of its kind. All right? This is like where the intermolecular forces come into play. What type of intermolecular force will diethyl ether experience with another diethyl ether? Well, you're right. All of them are going to experience London dispersion forces, but is that the strongest force? Why is it not hydrogen bonding? Oh. You have to have hydrogen bonded to oxygen, nitrogen, or fluorine. And none of the hydrogens are bonded to the oxygen, so therefore this is not going to be hydrogen bonding. What will it be? Dipole-dipole. Dipole-dipole. Obviously London dispersion forces as well, but the strongest force is dipole-dipole. What about ethanol? What's the strongest force it's going to experience with another one of its kind? Hydrogen bonding. And then what about water? Hydrogen bonding. But what do you notice about water versus ethanol? There's 2 areas for hydrogen bonding on the water, whereas only 1 on the ethanol. Okay? So now, based off of the structures, which one do we expect to have the higher boiling point? Water should have the highest boiling point. Does that match up with the graph? I don't know why I think it's supposed to be a degree sign. I think there's like the cursor was right in front of it when the screenshot was taken. I know, I'm sorry. But wait, this entire graph has nothing to do with boiling point, right? But it kind of does, because vapor pressure and boiling point are related. Okay? The higher the higher the vapor pressure, the more readily it'll go to the gas phase, right? Right? So, is this graph right? Yeah, no, sorry. Okay, it is. Sorry. This is measuring the vapor pressure of the liquid, and then at the temperature. So this is showing the boiling point. The vapor pressure, when you compare vapor pressure to temperature, it shows it. Let's look at all one temperature, though. Let's look at all one temperature. Let's look here. Okay? Like at 20 degrees, water has the lowest vapor pressure, whereas diethyl ether has the highest. Okay? So in general, the stronger the intermolecular force, the lower the vapor pressure. So you have to kind of look at, instead of changing vapor pressure, instead of keeping vapor pressure constant, let's keep temperature constant here. Water has the lowest vapor pressure at this temperature because it has the strongest intermolecular forces holding it together, whereas diethyl ether has the highest vapor pressure because they are going to escape to the gas phase the easiest. Right? So the weaker the force, the higher the vapor pressure. The stronger the force, the lower the vapor pressure. Okay? And the lower the vapor pressure, the higher the boiling point. Because the lower the vapor pressure means less of it wants to go to the gas phase. So in order to make it go to the gas phase, you have to put more energy in. All right, so looking here. Okay, I already talked about this. Looking here. It's what I already kind of said. Wait, is this right? Does this match what you have in your notes? Yes, it does. Okay, good. So vapor pressure is the pressure of the vapor present at equilibrium. So the system is at equilibrium when no net change, sorry, your packet says charge, no net change occurs in the amount of liquid or vapor because the two processes exactly balance each other out, which is what I was showing in this diagram here. That eventually it's going to become a constant vapor pressure. So what is the vapor pressure of water at 100 degrees Celsius, and how do we know? So what's happening at 100 degrees Celsius for water? It is boiling, right? So at the boiling point, fun fact, at the boiling point of any liquid, the vapor pressure equals the atmospheric pressure. That's why, like, when you look at a phase diagram, you can manipulate the boiling point of something by changing the overall pressure. You can make something boil without actually heating it up. You can do it by just changing the pressure. If you lower the pressure, it's going to boil much easier. Okay? Because you're basically bringing down the atmospheric pressure to what its vapor pressure is. So at 100 degrees Celsius, the water is boiling, and so therefore its vapor pressure is matching the atmospheric pressure, because we basically increase the vapor pressure by heating it up. Pressure and temperature are all interrelated, okay? So the vapor pressure of water at 100 degrees Celsius would be whatever the atmospheric pressure is, which typically is around 1 atmosphere. And we know because of this. Okay? All right, so measuring vapor pressure, we use, this has these diagrams. It's like a barometer, but instead of a vacuum here to measure the atmospheric pressure, we're actually going to somehow insert the gas right in there. What liquid is this? Mercury. See how it has the convex meniscus? Because it doesn't want to touch the sides of the glass as much as possible. All right, so water at regular, like at standard temperature, whatever temperature this is at, water is going to have the lowest vapor pressure, whereas diethyl ether is going to have the highest. That's what this is just showing, okay? Just another way. All right, I want to get to this formula. This is kind of what I was showing before. Liquids in which the intermolecular forces are large or strong have relatively low vapor pressures. And when you increase temperature, vapor pressure is going to increase significantly. And then there's our boiling point right here, when the vapor pressure matches the atmospheric pressure. All right, so Clausius-Clapeyron equation. I know, it's a funny name. The Clausius-Clapeyron equation. So this is how we can actually calculate. This should look similar to the, I think it's called the Arrhenius equation back in Unit 3, figuring out the activation energy based off of the rate constants. It's like almost the exact same formula, just different things are substituted in. So you could take, if you measured the vapor pressure at 2 different temperatures, you can find the delta H of vaporization, the enthalpy of vaporization. Okay? Or if you knew this, you could find the vapor pressure at a different temperature or whatever, okay? So we're gonna do a couple examples. We're going to do one example with this, just to show how we can manipulate this formula. Just please note that you have to use the joules R because we're doing something with energy, okay? And temperature always needs to be in Kelvin. So the vapor pressure of water at 25 degrees Celsius is 23.8 torr, and the heat of vaporization of water at 25 degrees Celsius is 43.9 kilojoules per mole. Calculate the vapor pressure of water at 65 degrees Celsius. So I'm just going to rewrite the formula since I know it's on the other page for you guys. I'm just going to put P1 over P2. This is the vapor pressure at temperature 1. This is the vapor pressure at temperature 2. Equals delta H of vaporization over R times 1 over T2 minus 1 over T1. Now, something else that I wanted to point out. Delta H here is given in kilojoules per mole. R was 8.314 joules per Kelvin mole. So what are we going to need to do? And does it matter which one you convert? No, as long as you get them both to saying joules or both saying kilojoules. Okay? So I don't care which one you convert. What are we solving for? We're solving for P2. We're solving for the vapor pressure at 65 degrees Celsius. So I'm just going to leave this as natural log of P1 over P2, and then I'll plug in P1 once we solve for this. Okay? I converted R 43.9. And then what is T2 in Kelvin? What's 65 degrees Celsius in Kelvin? How do you convert that to Kelvin? Add 273. So what is 65 plus 273? 338? And then T1 is what? 298. All right, so this way we can at least solve for whatever the natural log of that thing is. And then we'll get rid of the natural log and then plug in P1. When you do this, and I do want you to practice this on your own, I'm just going to keep going though for the sake of time. Make sure you can solve these formulas, okay? You should get negative 2.0969. And that's what the natural log is. How do I get rid of a natural log? Yep, e to both sides. So I'm just going to leave that, whatever I had in my calculator, and then do e to the answer. And I'm going to get P1 over P2 equals 0.1228. And then we know what P1 is, which is 23.8. And it doesn't matter what unit your pressure's in, as long as if you were given both pressures, you just need to make sure they're the same unit. All right, equals over P2 equals 0.1228. I'm going to solve for P2. Oh, I did something wrong. I'm getting 194. I think I just typed something wrong. Hold on. Did I put my the R value? You got 194? It just seems really high. Does anyone else feel that way? It just seems really high. You have no idea. I don't know, it just seems significantly higher than I want it to be. I'm looking up what I got past year. It just seems too high. I converted R correctly, right? Yeah, it should be -3. What did I do? Sorry about this. Let me just double check. Okay, I guess it is 194. Okay. It just seems it seems really high. But okay. We did the math right. So yay. Okay. Just a couple more things and then we'll be done. All right, so this is a heating curve of water. Heating curve of water. This question here is exercise 8, which is on the next page for you, but I want to talk about the heating curve first. Okay? So what do you notice about this curve? What are some things you're noticing? What? Yeah, this is showing the different phase changes. This is showing the temperature at which the different phase changes occur. So heat is being added, so energy is being added at a constant rate. But is the temperature changing at the same rate throughout? No, what do you notice is happening to the change in temperature at certain points? It stops for a little bit. At the phase changes, do you notice how the slope of the line becomes 0? but yet heat is still being added. So for example, we have ice, or solid water. It starts off at negative 20 degrees Celsius. That's really cold. I don't want to be in negative 20. We start heating it up, and then what's occurring at this phase change on the molecular level? The intermolecular forces are being overcome because the heat going in are now, instead of heating up the molecule and making them move faster, it's overcoming the forces. And then once they're all overcome, then the molecules start heating up again. They start moving faster and faster and faster until they overcome their intermolecular forces completely. So going from solid to liquid, it's like those forces weaken. Going from liquid to gas, they are completely overcome. Bottom line is substances cannot multitask. They cannot multitask. They can either change phase or change temperature at the same time. I'm going to simultaneously. I ran out of room to put simultaneously on there. Okay, so which one do we expect to be larger? Delta H of vaporization or delta H of fusion? By the way, fusion is melting. And then vaporization would be boiling. So do we expect the amount of energy that it requires to melt water to be greater than or less than the amount of energy it takes to boil water? But which one do we expect to be greater? Vaporization. Delta H of vaporization should be larger because we're completely overcoming those forces. Yes. Yeah. It's not just water. It's going to be true for all and this was a given substance. I specifically said water because it had to do with the heating curve. But any substance, the delta H of vaporization should be greater than that of the fusion, okay? Because those intermolecular forces still play a pretty big role in liquids, whereas they don't in gases, okay? And the next thing is solutions, right, on your page? Like I didn't skip over anything? Yeah, so the next thing, solutions, which is going to be the next video. Wonderful.